Right, so now that we have run our regressions, we need to move on and look at the assumptions of those regressions. So as we've already spoken about, regression has this straight line that it creates, and it makes the assumption that the difference between 0 and 1 on this straight line is the same as 1 and 2 and 2 and 3 and so on. So this equates to one of the assumptions, the assumption of linearity, so we need to first of all demonstrate that that makes sense. Other assumptions that come with regression, so other underlying expectations of this analysis, is that we have an independence of error. And so what this means, quite simply, is that no single data point is going to tell us anything about any other data point. So the easiest way to think about this is simply that nobody was sampled twice. Generally speaking, we simply say this was met by design. There are very specific tests that have been developed that can account for designs that violate this assumption. We're not looking at that today. But it would be very, very clear from the setup of the research whether or not this assumption's been violated. We then have an assumption of normality. Now, this assumption is not the normality of your dependent variable or your IVs like we looked at earlier, but instead it's the normality of the residuals from the regression. And now a residual is quite simply the difference between what the regression thinks a person would get, so their expected outcome, their expected DV score, and their actual score. And so we expect that these differences are normally distributed. And so to assess this, we're going to be using histogram, Shapiro-Wilk, a new kind of graph called p-norm, but these are generic statistics and graphs that you could be using for any kind of normality assessment. We're just applying it to residuals. As I mentioned before, we have the assumption of linearity of residuals. So this is essentially the assumption that our regression line is the best line for our data, and it goes through the middle of the data, or at least the data follows that line. We're going to assess this using a residuals versus fitted scatter plot, or an RVF plot, that is effectively going to put our residuals on our y-axis, and then on our x-axis we're going to have all of the different predicted scores from the regression. But I'll talk about more what that graph looks like when we get to it. And the last assumption is the assumption of homoscedasticity. This is also known as constant variance, and this is constant variance of residuals. Sometimes homoscedasticity is spelt with a C instead of a K. And this is the assumption that our residuals will vary at a relatively constant rate along our regression line. So we're also going to use the RVF plot for this, the residuals versus fitted scatter plot. Now, to actually get all these assumptions, we need to use post-estimation commands. So post-estimation commands can only work following a certain analysis or a certain command. So, for example, we're going to use RVF plot, and the RVF plot command draws information directly from the last regression that was run. What this means is you can't run 3 regressions and then run the RVF plot and expect to get 3 lots of graphs. You'll only get one at a time. So we need to rerun our regression first. Then we use RVF plot with the y line and then in brackets 0 subcommand. This is actually going to put a nice thick line through 0 on this plot, which, as I'll explain in a second, is effectively your regression line. Okay, so let's run these commands and grab our RVF plot and we can go from there. So this is what our plot looks like. Now if I just bring up Paint, what I would like to show you, before we spoke about our regression looking a little bit like this, right? Effectively what happens in an RVF plot is that instead of this line being on an angle, it's moved so that it's horizontal. So really the axis kind of goes like that. If you like, well, not quite like that, it'd be more like this in our case. But effectively what's happening is we're rotating the graph. We still get a normal axis like on the black, so really what we would be seeing, what we are seeing is this. And if I bring up our output, which is just there, I've even got the right colors. But effectively what this red line is the line from our scatter plot from before. It's just been put on its side. And so now what we're looking for with this graph, we're assessing linearity and homoscedasticity. So for linearity, all I'm expecting is that my dots pretty much just follow the line. And if we look at the graph, that's what we see. Generally speaking, our dots are just following the line here. What would be a problem for linearity is if our dots actually went something like this. Start above, they go down, and maybe they come back up again. And this would suggest that actually a curvy line would be a better fit than a straight line. And that's important next year when you move on to third year statistics, if that's where you go. This is a potential analysis you might be looking at, or in future stats courses. Another potential problem with this kind of graph is if you get this kind of effect happening, where really, rather than the data points following this red line, they're actually going like this, off on an angle. Okay, that's linearity. Now, homoscedasticity is all about this assumption that our data points vary at a constant rate. So what this means is effectively, if I'm getting scores up to about 15 here, I should really have them at about 15 down here as well. The bigger issue really, like this looks fine to me. I know we don't literally have about the same range, but this looks perfectly fine. I'd be happy with this. What is actually a bigger issue and what you're actually looking for is what we call fanning. So this is what fanning looks like. And fanning, I guess, is called fanning because, well, if I draw lines, it kind of looks like a fan that you might hold and wave to cool yourself down. And it could be going in the direction that I have, but it could also go in this direction as well. So fanning can go in a number of different directions. And the issue with fanning is it means that you have very little variance on one end, but a lot of variance on another. Here we don't have that. I know that this kind of looks a little bit like fanning, like if I was to just screenshot this and put it into Paint. I know that this, oh, okay, all right, let's try that again. This kind of looks like fanning, but really in the context of what we're doing, it's perfectly fine. Because it's actually quite simply due to this one dot here. And if I got rid of that dot, as much as I can, it would otherwise look like a perfectly fine distribution. So it's not really the issue of that one dot. It's not a fanning issue. We just have a single point that's making it look like that. So it's otherwise perfectly fine. When you're looking at this, if you want a really cheap way of assessing linearity and homoscedasticity, the cheapest way of doing it is simply saying, for linearity, does my distribution on the top kind of look like the distribution on the bottom? And that we're seeing there's some points that are close to the line, there's a couple that are far away. Down the bottom, points are close to the line, there's a couple that are far away. We get this symmetry above and below. So this looks perfectly fine. If we had that U-shape happening, then I'd have points here and nothing in the middle, but then nothing here, and points in the middle. They wouldn't be symmetric at all. And then for homoscedasticity, I would essentially put a line down the middle and go, does my left look like my right? And here I have points around here, on my right I have points around here. If I had fanning, I'd have very few points and then lots of points over this side, or the other way around. So you can do this sort of split half mirroring eyeballing effect to try and see what's going on. Doesn't always work, but it is a quick way of making that assessment. Okay, let's go back to normality. So the first thing I need to do is I need to extract my residuals from my regression. So to do this, I need to use the predict command. And then I give a new variable name. So I'm going to use RQ1 residuals. You could use whatever you like. The thing is, we have 3 regressions that we need to create residuals for. So each one needs a unique name. You can't actually write over the top. Stato will just throw its arms up and go, nah, sorry, not doing that. So I've used RQ1, RQ2, and RQ3 to represent the different research questions. So predict, a new variable name, comma, and then resid. And that tells Stata that what we're doing is we're predicting the residuals from the regression. I'm then going to use a histogram command to get the graph for the residuals, the histogram for the residuals. I've already played around with this and figured out that a bin size of 10 looks pretty good. And then I'm also going to grab my Shapiro-Wilk. We'll come back and do the p-norm after that because it's a second graph and Stata won't show us 2 graphs at once. So this is my distribution. Now, I know it looks a little bit bimodal. You know, we have this here, and then we have this up here. But really, this looks perfectly fine. It's not totally realistic to expect that you'll get lots of data around 0 on a regression line. But this looks fine. If I go and look at my Shapiro-Wilk also tells me everything is fine. But if looking at those two things, I wasn't certain. I could, if I wanted, go and look at the summary stats. So we're not going to do that today. We're going to look at a p-norm. Now, a p-norm effectively gives you a line that would represent a normal distribution, and then little dot points that say at each sort of point along here, how normal or how close to normal is your distribution. And effectively what you want is these dots to basically be on top of this line. What you don't want is snaking, and snaking is when the dots sort of come up and then go down and then come up and then go down. And so we have very, very minor snaking. We have some snaking going on here. This really isn't ideal. It happens, it's not the end of the world, but it's not drastic snaking. Like, if it was really, really bad snaking, what we would actually see looks like this. Nope, don't want to save. Let's make this a bit thicker. We see a line go like this, and then our dots will go like this. Like, we're talking extreme snaking. I've probably gone a little bit over the top with that, but you sort of get the idea. It's a bit more than this. This is quite minor. Okay. So based off that, it looks like the assumptions are perfectly fine. Very quickly, if we do research question 2 now. Again, this looks perfectly fine to me. The top looks very similar to the bottom, and there's no real evidence of fanning. So linearity is met, and so is homoscedasticity. This doesn't look too good. It looks very platykurtic. But again, we have a very, very small n, and there's really no signs of skew. But let's go and have a look at our Shapiro-Wilk. It's coming up non-significant. This is good. We do have a small sample size, so I don't want to rely just on my Shapiro-Wilk. p-norm has a little bit of snaking, but is otherwise perfectly fine. So again, I think these assumptions are fine. And I hope what you're noticing that I'm doing here is I'm not just going, oh, look, there's a problem. What I'm doing is saying, okay, there's a little bit of an issue, but it's probably not a big problem. What would be more of a problem is extreme violations, and that's really what we're looking for here. Now, very quickly, if we do the final research question. Again, this looks perfectly fine. This one point down here is a little bit problematic, but look, again, I wouldn't be too fussed. We have homoscedasticity, both sides look fine. Linearity looks perfectly fine as well. The top and bottom are very similar. Now if we look at normality, this looks very nice. I'd be extremely happy if I got that in my own data. If we look at our Shapiro-Wilk, that is so far away from being significant. That's basically 1. I wouldn't even need to do the p-norm, but we'll do it just for the sake of it. So you can see a little bit of snaking, yet Shapiro-Wilk was extremely non-significant, and the histogram looks perfectly fine. So again, this is just further evidence that this small amount of snaking is really not a problem. So in all 3 cases, I think all the assumptions have been met. Now, if I was to conclude, and we'll just do a conclusion for ratings and research, the way that I would have written it up, that my statistical conclusion would have been the chance of obtaining a t-statistic, so we're down here, the chance of obtaining a t-statistic of 2.88 on 22 degrees of freedom, if the null hypothesis was true, is 0.9% of a chance. This is less than our definition of sufficiently unlikely, which is 5%. The real-world conclusion, so what this actually means, is therefore there is evidence to suggest that for every 1 hour of research put into planning a project, a student's rating for the project by the judges would significantly increase by approximately 5.75 units. I also provide the confidence intervals. So I'm giving the confidence intervals and saying approximately, because really it could be anywhere between 1.61 to 9.9 unit increase for every 1 hour. Just generally speaking, what we're seeing from the data is it's on average about 5.75. But there is actually a bit of wriggle room there. Cool, that brings us to the end of simple linear regression.